Hey guys, Mr. B here, and in this video we're going to be going over chapter 5.2 and talking about electron configurations. So this section we're going to be learning about how electrons are placed or configured around the nucleus of an atom, and there's going to be a lot of weird words. Okay, so vocab here isn't super extensive, but there's just some weird things. I will do my best, like I said, to explain how this stuff works. But ultimately, if you have any questions, make sure that you do ask during class or through email. Okay, so let's talk about electron configurations. So basically what we're going to be talking about here is where are electrons around the nucleus. Okay, it's kind of like if we had to give an electron an address for where is it around the nucleus, that's what electron configurations are. Okay, they look weird. There's some numbers and symbols and stuff, but each thing, each piece of it represents a different portion. Okay, so we're going to talk about how they are, how they work, as well as how we write them. And there are 3 rules when it comes to writing out an electron configuration and where the electrons are. Okay, the 3 rules we have are the Aufbau Principle, the Pauli Exclusion Principle, and Huns Rule. And each of these 3 principles, these 3 rules, will tell us how electrons fill orbitals around the nucleus of an atom. Okay, so first off, let's talk about the Aufbau Principle. So the Aufbau Principle is basically a rule that says when electrons start to occupy orbitals around the nucleus of an atom, they will always do so from lowest energy orbitals to highest energy orbitals. Okay, now this little picture here is a diagram that represents all the different orbitals that exist from lowest energy to highest energy. So down at the very bottom, we're going to see 1s. Okay, and actually, you know what? I'm going to try to see if we can zoom in here so that we can see this a bit better. Perfect. There we go. Okay, so this is a lot better. Okay, so we have 1s. Okay, the 1 means the first energy level. Now, I'm going to try to even break it down even further for you. For what does that mean? So we're going to bring up the Bohr model of the atom because it's going to help us understand. Okay, so when we talk about energy level, we are primarily talking about the radius or the distance that the electron is away from the nucleus. Now the Bohr model was 2-dimensional. Okay, it's a circle. And remember that when we're talking about orbitals, we're 3-dimensional. So just imagine it's a sphere, okay? And it's a certain size. So 1s means that we are in the first energy level. So we are in this first ring, okay? This first small circle. And we're in an S-shaped orbital, so it's a sphere. That's the lowest energy. So if we were to put electrons in orbitals around the nucleus, we always have to fill up that orbital first in that energy level. Then the next one is the second energy level, and is still an S-shaped orbital. So second energy level now is the second ring. So we're a little bit further away from the nucleus, and we are still filling up a spherical shaped orbital. And then after that, we move to the p orbitals, still in the second energy level. So now we again are still in the second energy level, okay, same radius, but we're now filling up p-shaped orbitals, which are the peanut-shaped ones, okay, not the sphere-shaped ones, because that one's already filled. Then from there, we go to the third energy level. So now we're further away from the nucleus. Okay, now we're further away. And we're filling up the S-shaped orbital first, then the P-shaped orbitals. Now, after this point, things start to get a little bit more weird. Okay, and this is where I really need you to understand how this works. The energy level, 1, 2, 3, 4, 5, and 6, doesn't actually pertain to the amount of energy it has. Okay, the energy level primarily means how far away from the nucleus are you? Are you close? Are you further or further? Okay, I know it's very confusing because it's called an energy level, but it doesn't actually pertain to energy. And here's what I mean. If we look right after 3p, we see 4s. 4s is lower in energy than 3d orbitals. Okay, so energy level 4, S-shaped orbital, has less energy than energy level 3 D-shaped orbitals. And this is where, again, I'm trying to explain to you. Because, of course, energy level 4, you think, well, it's the 4th energy level. It should have more energy, right? It's energy level 4, not energy level 3. It doesn't matter. The energy levels are more about radius, how far away you are. So at this point, energy starts to get a little bit staggered. So after the 3p orbitals, we have the 4s orbital. Then the next higher one up is the 3d orbitals. Then we have the 4p orbitals. And then we get to the 5s orbital, and then 4d orbitals, and then 5p orbitals, and then 6s. And so it starts kind of getting diagonally staggered like this. Either way, there is a way to determine the order by using the periodic table. Okay, so you don't need to memorize this. There's another video of me going over the periodic table and how you can read the periodic table to know this order, so you don't need to like memorize this. The main factor here is just understanding that we have to fill up electron orbitals from lowest energy to highest energy. Okay, and there's a specific order that you have to go. You can't skip stuff. So if, for example, we put electrons in the 2s orbital, we can't then go straight to the 3s orbital while leaving these ones blank. Okay, we have to fill these completely up first. All of these orbitals have to be completely filled before the next electrons will go to the next orbital. That's what the Aufbau Principle says. So hopefully that makes sense. Again, I'll probably explain this more in class, but that's the gist of it. So, okay, the second rule, the Pauli exclusion principle, basically says that at most, any orbital can only have 2 electrons in it. Okay, so maximum number of electrons you can have in an orbital is 2. And if you do have 2 electrons in an orbital, they have to be spinning in opposite directions. So electrons, a lot of times, are constantly spinning. Okay, they're either spinning clockwise or counterclockwise. Or a lot of times we'll denote them as spinning up, okay, spinning up or spinning down. And so if you have 2 electrons that are paired together in an orbital, so you have 2 electrons in an orbital by each other, they have to be spinning opposite directions. So one's going this way and the other's going this way. Okay, they're not going to both be going in the same direction. They have to be going opposite directions, which, by the way, try doing this with your fingers, and it's very difficult. So that's the Pauli exclusion principle. And again, we'll see more of this when we get to some example problems. Okay. All right. And then the last rule is Huns Rule. So Huns Rule states that electrons will occupy orbitals of the same energy in such a way that all of them will have the same exact spin to make spin as large as possible. Now, what the heck does this mean? So here's a better way of explaining Huns Rule, okay? Huns Rule basically says that when you start putting electrons in orbitals, you will first put 1 electron in every orbital that you can before you go and put a second one in the same orbital, okay? So imagine that we have the p orbitals. There's 3 p orbitals. So, we have 3 orbitals, right? 1, 2, 3. We'll put 1 electron in each of them first. We're not going to put 2 and 2 and 2. And the reason for that is electrons, remember, have the same charge. They're all negative, right? And as most of you probably know, similar charges repel. So if you have 2 electrons that are both negatively charged and you bring them near each other, they're going to want to push away. So they don't want to be next to each other if they don't have to be. So if you have 3 orbitals, right, 1, 2, 3, and you can put 1 electron in each so that they're not next to each other, that's more ideal than taking 2 electrons and putting them together right off the bat. So Huns Rule basically says you're going to put 1 electron in each orbital first. Then we're also going to make sure that each of those single electrons are all spinning the same direction. So they're all going to either be spinning up, so spin up, spin up, spin up, or spin down, spin down, spin down, or clockwise, 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 or counterclockwise, counterclockwise, counterclockwise. Not this one's spinning up, and that one's spinning down, and that one's spinning up, or that one's up, and that one's up, and that one's down. They're all going to spin the same direction. Again, this will make more sense when we get into some example problems, okay? But those are the 3 rules. So here's a chart, and I'm going to zoom in again on this so we can see it better. And this is going to kind of show this, right? So these boxes are representing the different orbitals. We have a box here for the 1s orbital. We have a box here for the 2s orbital. There are 3 p orbitals, so there's 1 box for each orbital. So here's the px orbital, py orbital, pz orbital. Px just means this is the p orbital that sits on the x-axis. Py, that's the p orbital that sits on the y-axis. And pz is the one that sits on the z-axis, which is, again, the axis that goes straight out and straight backwards. And then we have a box for the 3s orbital. These arrows are representing the electrons. So let's look at oxygen, for example, okay? Oxygen has a total of 8 electrons. We know that because oxygen is element 8 on the periodic table. We can even pull this up and I'll show you. So let's pull up a periodic table. So oxygen is element 8 right here. Okay, so it has 8 electrons. It has 8 protons, but it also has 8 electrons. And if we look at the number of arrows here, we see 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 electrons. And so the first 2 electrons are going to be in the 1s orbital because the Aufbau principle says that's the one you have to fill up first before you can fill up higher ones. There are 2 electrons there. So Pauli exclusion rule principle says you can't have more than 2 electrons in a box, right? So there's only 2. There's not 3 arrows. And they have to be spinning opposite directions. So one's pointing up, one's pointing down. All right? So there's the Aufbau and the Pauli exclusion principle at play. After the 1s orbital is filled, then we go to the 2s orbital. And again, we fill 1 electron, 2 electron. Spinning opposite directions, that one's filled. Then we get to the 2p orbitals, which are these 3. Okay, so 1, 2, 3. These 3. And now, here's where we'll see Huns Rule come into play. And in fact, we see it better with nitrogen. But regardless, we're going to have 1 electron placed in each orbital first before we go back and put a second one and pair one of these up. Okay, so if we look at nitrogen, we'll see it better. So we see that we have 1, 2, 3 electrons that are each individually placed in orbitals first, and they're all spinning the same direction, right? Up, up, up. Now, or they could be down, down, down. They just happen to draw them upwards. And then once we have more electrons, then we will go back and pair them up if we have to. Okay, so oxygen has a total of 8 electrons. So first we put 3 in the p orbitals, and then we have 1 that we have to go back and put in the first p orbital again to pair it up. Okay, now if we had more electrons, then we'd pair up the next one, like we see in fluorine here. If we had another one, we'd pair up the next one, like we see in neon. And then once they're all filled, like we see down in sodium, once these are all filled, then we can move on to the 3s orbital and put electrons there. Okay, so this kind of showcases all of those 3 rules. And then we would write, again, what's known as the electron configuration, which is essentially like the shorthand way of showing where all these electrons are. So for oxygen, we have 1s, and there's a little 2 as an exponent. The 2 is showing that there are 2 electrons in this 1s orbital. Then we have 2s2. 2s is, of course, the 2s orbital, and the exponent, the little 2, is that the 2 electrons in there. And then 2p4. So we have electrons in the 2p orbitals, and there are 4 of them, right? So 1, 2, 3, 4. This is our electron configuration, this thing written here. And all the boxes and stuff shown to the left, that's what we call an orbital diagram, okay? Where we actually like physically draw in arrows and actually show them that way. A lot of times, though, we're not going to draw orbital diagrams because they take more time. It's a lot faster to write out an electron configuration. And again, there's another video of me going over how we can use the periodic table to determine this, because at this point, you're probably wondering, how the heck do you even know to do this? The periodic table tells you, okay? So there's a video of me showing you. Just watch that one after this. It will make more sense. All right, so that is the end for part 1 of this video. Part 2, we'll be taking a look at some examples of writing out electron configurations, as well as some exceptions to the rules when we have elements that have some weird things that they do. So I will see you